In exercise 1D, we will talk about regularization for artificial neural networks, especially about weight decay, dropout, and early stopping. So let's first talk about weight decay. Weight decay is basically like ridge regression or lasso regression or ElasticNet. You have your loss function for the neural network, and we apply a penalization term, so L2 or L1 penalization, and thereby reduce the weights of our, or the size of our weights by penalizing that. And this way some weights could be even reduced to 0. Now dropout is a little different. So if you think back to the lecture, dropout is that you drop neurons from the network and thin out all the layers in the training phase. So for every run in the training phase, we will have a predicted or a predefined probability P. So we set this before as a hyperparameter of how likely it is in a knot that a neuron will disappear during the training phase. So for one unit, one training unit, for example, one batch, we will this will disappear, and then after after every batch, we will basically reevaluate: is now this not going to appear with this probability, or is it not going to disappear? So this way you have like a similar size every step during the training of the network, but the constellation of the network will be vastly different. So, but during the or after the training, once you've trained the network, all the knots will be present again, and obviously we have to adjust these then with the probability to have the same expected output or expected prediction in the end as in the training phase, because now basically if you have a probability of dropping out of 50%, then you will have after training a full network which is double the size of the single training networks. So you have to adjust for that and multiply the single weights with the for example with 0.5 if the prediction was the probability of dropping out was 50%. So by dropping, why do we do this? Why do we throw out knots randomly? Well, this has the reason that during the training these knots could rely too much on other knots basically, and by dropping this single knots from the training from the network during training, we have to get these knots to be more independent of other knots, and this way we will have a regularization effect, because they cannot as easily, due to this variation, model to the so basically fix modeling to the data. This would be overfitting, because the nodes are always changing that they get their information off, and this way this prevents basically this um, adapting to the training data, to these idiosyncrasies, because it's so um, varying all the time. This is a lot like random forests, where we dropped features for all the for the trees. We, if you think back, we have different sets of features for the single trees, and then by adding them up, they decorrelate. So this decorrelation is basically independence of single nodes. Okay, last is early stopping. And that's the easiest one, because if you think about it, we have more than one pass through the whole training data. And one pass through the whole training data we call an epoch. And we do many epochs to train the network closer and closer to the training data. And well, if we train it too long, then it will overfit, because it will fit too close to the training data. But we can calculate our out of sample metrics after every epoch. So after every epoch, we get our out of sample metric and our in sample metric, and we see how the errors progress. And at one point, we will see, that both will decline, or that's what we wish for, is both the in sample and out of sample error will decline. But at the point of overfitting, the out of sample error will rise again. So we want to have to quit or to stop before this point is reached, where the out of sample error is rising again. And this we can do by early stopping. That basically says, okay, when the out of sample error is rising, we want to stop before that. And it basically saves the networks before that, and then it will pick one of the trained networks. So the weights basically after that procedure as the perfect or the optimal network. So if we let's say we train our network, and after 50 epochs we see, okay, now the out of sample error is rising again, and the best training was, or the best out of sample we had was at well, at this point, at run or epoch number 50, then we would choose this network. But sometimes it can be that it won't be like a perfectly parabola where you have like this decline of out of sample error and then it's rising again, but it might have like some bumps, or you have like this kind of irregular decrease where it's rising again, then it's falling again, then it's rising again, then it's falling again, but overall it falls and then somehow it will rise again. So you want to have some kind of delay. So maybe you wait for a certain of epochs before deciding, okay, now we have to interrupt the training. So this would be called patience in this setting. So let's say we will have so we will train our data until run number 50, so epoch number 50. Then we see, oh, now we actually don't improve. The out of sample metric is getting worse, it's rising, like the out of sample error is rising. Then we will say, okay, let's wait for 10 more epochs, and if the out of sample error hasn't fallen below that, below our best out of sample error before epoch number 50, then we'll stop at epoch number 50. Otherwise, we will go on training. Okay, this is basically what this patience says. And then we also have to define a margin, because we don't want to say, well, if we have, let's say, out of sample error 50 at epoch number 50, I don't know why I like the number 50 so much, but let's say our at epoch number 50 we have an out of sample error of 50, and then at epoch number 59 we have an out of sample error of 49.9, then it didn't improve much out of sample wise, but we have trained further and it is not likely to improve that much further. So we want to say, okay, it needs to have a certain margin to improve, that we won't stop at 50, let's say. Okay, so again, early stopping is just when the once the out of sample metric does not improve for a certain amount of time, so for a certain amount of epochs, by a certain margin, then we will stop the training.